So, good morning to all of you, and welcome you all to the day three of 1 week online faculty development program on machine learning concepts and applications. So, friends, today on 16th of March 2023, the first session which we have now, that is on the CNN models for the classifications of images. So you will get the knowledge regarding deep learning, how the CNN models can work for the classification of images. And for this session, today we have Dr. Nishant Jain. He is MTech and PhD from IIT Roorkee. And at present, he is working as assistant professor in Department of Electronics and Communication Engineering, JP University of Information Technology, Solan, Himachal Pradesh. Dr. Nishant Jain, his research interests include image processing, machine learning, as well as of Internet of Things. He has published various papers in SCI journals, and presently he's guiding 3 research scholars. These scholars are working in the areas of medical image processing and hyperspectral images. He has given various talks in faculty development programs, workshops, webinars. And the best part of his profile is that he is an active YouTuber, and he has already uploaded more than 100 videos on his YouTube channel. I hope he will also share the link of his YouTube channel here in the chat box, and so that you people can also subscribe that channel. Moreover, he is a member of the Center of Excellence in Healthcare Technologies and Informatics and Technology, Incubation and Entrepreneurship Development Cell at his university, that is JP University of Information Technology. So I welcome you, sir, in this 1 week faculty development program on machine learning concepts and applications. And I hope the participants who have joined us from the various parts of the country, they will definitely learn, they will definitely know that how we have to apply the CNN models for the classification of images. Thank you so much, sir, for sparing your time and for accepting our request. And now I request you, sir, to start with your presentation. Thank you so much.
Thank you, Dr. Saurabh, and thank you for giving me the opportunity to interact with the participants. So, like this presentation, like I kept this presentation for the audience, like who have some background or who may not have any background about the images and about the classification. So I am going to give you an overview, like how the images, how we are going to acquire the images, and then how we use classification to make a prediction. And while doing so, I will also, at the same time, I will also try to include how we humans do the classification, means how whenever we see anything through our eye, how we make a decision. So because whatever like classification theory is there, it is just like inspiration is from our biological system. So I am also going to make you realize that how we are doing it and how the same thing we are trying to replicate through the methodology, through mathematics, through programming. So first of all, I will start with how we acquire the images. So to acquire the images, like all of us know that the images, they are consist of the pixels, right? Now what a pixel is. Now if you look at this particular unit, this unit has one sensor and a ADC, analog to digital converter. Now in each and every pixel, they have some capability to sense the input energy. Like this input energy, it can be the light, it can be X-ray, it can be MRI, it can be radio frequency, it can be ultrasound, It can be anything. So if we design this sensor to have a capability to sense the visible rays, then this sensor is going to produce the voltage signal corresponding to the visible signals only. And then because we at the end we need to store the image in the form of digital. So to convert it into the digital, we use ADC, and with the help of this ADC, this analog value is converted into the digital value, right? So the visible light that we are able to see from our eye, with the help of this sensor and ADC, we are able to convert it into a value. And why value is required? Because the all the images we need to process through our computer, and our computer, it is a digital device, it can understand only numbers 0 and 1. So just if we put this assembly in this form, in a grid form, like this assembly, I put one assembly is this, one is this, second is this, third is this, fourth, and so on. So if I use large number 81 sensors or pixels, and I arrange it in this grid form, in the 2D matrix form, then I will be able to form an image. How? Like this. Suppose if this is the object, when light falls on this object, it is going to reflected rays, it is going to fall on the sensor, and this sensor is then convert this visible light into the numbers, right? And these numbers then can be represented in this form, and you can see that over here 255, and it represents t, whereas all the remaining values, they are 0. How we get 0 and 255? This over here you can see that, coming back to this, if we have input energy and analog sensor has converted it into the voltage signal. So if the maximum voltage allowed is 5 volt and the minimum voltage is 0 volt, then ADC is going to convert it into digital value, right? Now when ADC is going to convert into digital value, it is just going to put a range that if it is 0 volt, then the digital value will be 0. If the value is 5 volt, it maximum value, it will be digital value will be 255, and all the voltages in between, they will have a digital value in between 0 and 255. So if there is a black light, we represent it with 0. If it is a white light, we represent it with 255. If it is some gray shade, then simply we represent it as 30, 60, 90, and so on, as per the brightness in the pixel value in the light, right? So finally I get this image. Now since I get this image, so for the human beings, for us, image looks somewhat like this, but for a computer in which we have stored the image, for a computer, image is just a number, it is just a matrix like this. So for a computer, image is not like this. Computer is not going to see the image like this. So what it means that since computer can understand only numbers, and for a computer image is in the form of matrix, so we need to apply some matrix operations. We need to have some processing to this. We need to apply some processing to this matrix so that we can extract some features. Extract some features means, suppose if I need to determine if there is a square of white circle in this image or not. So if I look at the numbers, you can see corresponding to white square, we have 200 values. Okay, 200 value. Corresponding to this gray shade, we have value 50, and corresponding to black, we have value 0. So just if we do some programming on this, then simply if I want to detect the white area, simply since the value of this 9 pixels or 9 squares, since the value is 200, they are same, so I can consider that it belongs to the same object, and the object is a square, right? Similarly, I can say that since all this value is 50, so the shape of this is somewhat like this one, right? And so on. So it means overall what we can conclude that image, for a computer, image is a digital values, and it is in the form of a matrix. And to process the image and to do any prediction, we need to manipulate the pixel values. We need to get information from the pixel values. Now, as I told you, this same assembly can be used to scan images for different purpose. Like if this input energy, if it is X-ray, means if we design the sensor in such a form that our sensor is capable to sense X-rays, then we will be able to get the X-ray image. If our sensor is capable to sense RF signal, then we will be able to get a MRI. If it is capable to sense sound signal, we will be able to get ultrasound images. If sensor is made to sense IR radiation, we will get thermal images. So the main concept behind the acquisition of digital image, it remains same. Only difference is that once we get the images, then we need to put some idea about the processing. And the processing for different images, it can differ from one modality to another. Means the idea that I can put, the processing that I need to put on ultrasound image, it can be different, and for thermal image it can be different, because as you can see in this image, the like as we already like whenever we see any ultrasound images, it is very difficult for us to put any idea if there is what is the location of different organs in this. But doctors, they are capable of doing it. Why they are capable? Because they have studied about this, and it is their domain expertise that they, with the help of like this curve area, they can have some idea that what this curve in this image is means, right? So they can put some idea, and they can detect if what type of organ is present in this and what type of abnormality is present in this. Whereas in this, we can see that there is some human, and like over here there is some camera. So the processing that is required for this, it will be different in comparison to this. So, but again, the concept, the steps that are involved in processing the ultrasound images or thermal images or X-ray images or any images, the flow of the methodology, it will remain same. Right? Now for the color images, since as we know that color images, it consists of 3 colors. As we know from our school days knowledge, that if we combine 3 colors, red, green, blue, in different proportions, we can have any color, right? So, and the same thing we can check from the paint software that is in our Windows, right? So simply by changing this value, we can have different colors. So it means that if I want to have a color image, I need 3 information. One information is about the red color content, second for the green color content, and third for the blue color content. And then all this together with the help of these 3, I will be able to get the color image. But again, this color image, it is visible to me. It appears to me like a color image, but for a computer, it will be a matrix. But for a for these images, matrix will be 2-dimensional, only rows and columns will be there. But for a color image, since we have 3 layers, 3 information, one for red, green, and blue, so the matrix size, it will be 3-dimensional. Okay, rows will be there, columns, and there will be 3 layers. So 3rd dimension will also be there, right? So so overall, what we can conclude, that image is just a matrix, and matrix operations can be applied on it to extract the information from the image. Now coming to the processing part, especially like how we can do the prediction, or how we can classify that whether the image consists of like some animal or some human, or some prediction about the abnormality in the medical images. So what is the flow or pipeline of that classification? So we can have 2 types of approaches to do this. One is the classical approach, another is the CNN model based approach. And first of all, I will discuss classical approach, because this same classical approach, when we automate it completely, then it becomes CNN model. Okay, so we like with the classical approach, I will be able to make you realize that how we humans make a decision. And same thing we are trying to put in terms of mathematical model so that we can write a program to predict or to enhance the image or to process the image. So starting with the classical approach. So classical approach for image classification, it consists of these five things. First, we need to have the image as an input. From the image, we extract some features. Then from the extracted feature, we are going to select some features, and then that selected features will be passed to the classifier for training purpose, and then trained classifier will be used to predict the class of the new class of the new image, right? So it is going to predict the label of the new image. So what are all this? So let us discuss one by one. Now over here, coming to the feature extraction. So to give you the concept behind the feature extraction, I just want to ask you one question. Like, could you identify? We have two waveforms over here. So could you identify what is the difference between the two waveforms? You can put your answer in the chat box if you would like to do it. Yes, the if you see the shape of these curves, these waves, it is exactly same. The only difference is the range. That for this the range is from -10 to 10, and for this it is from 100 to 200. So just if I want to classify, if I want to differentiate between these two waveform, so the only way I can differentiate is with the help of the range. Okay, so this will be one of the feature with the help of which I can discriminate. I can tell that if the wave belongs to this category or this category. So range is one of the feature for this type of a signal. Now over here we have another waveform. Like we all know that it is a sine wave. Could you tell us anything about it? That what is this? What type of waveform it is? So over here, like it is simple to detect that it is a sine wave. But if we look at this, it is like quite difficult to determine that, or it is quite difficult to give name to this waveform. But if we take a Fourier transform of these two signals, we know like that if we take a Fourier transform of this sine wave, then it will give you only one amplitude corresponding to the frequency that is present in this sine wave. Okay, so overall, from this particular graph, what we can determine that because we just have one amplitude at only one frequency. So from this, we can conclude that the wave, sine wave, that this consists of only one sine wave. But in this, when we take a Fourier transform of this, we get this. And since the amplitude of this both of these two are same, but they are located at different frequency. So, but only two frequencies are there. So what we can say that overall we have this wave, it consists of two sine waves. So simply it consists of a two sine waves. And how, like looking at this waveform, it is difficult to determine that it consists of two sine waves. But if I transform it into the Fourier spectrum, then looking at the spectrum, it is quite easy to determine how many frequencies are there. And just it means that sometimes to get the information about the image or the signal, we may need to perform some transformation. And by transforming, now it is quite easy to conclude that how many frequencies are there. So suppose if someone give me this some waves, okay, and I want to determine if the wave belongs to this category or this category. So simply what I am going to ask the person, I will ask the person that simply get the Fourier transform and tell me that this impulse, like for how many frequencies you get the impulse. So if the person say that the person is getting the impulse for only one frequency, simply without looking at the sine wave, I can declare that it is a sine wave. If a person say that it consists of two frequency and both the amplitudes are same, so without looking at this, I can declare, I can conclude that it consists, the waveform must be having two sine waves and so on. So what I mean that without looking at the sine wave, because our system, it is a digital device, and as I told you that it can understand only numbers. So this waveform, it is also not visible to the computer. It is also numbers for a computer. So, but if I somehow get some quantitative parameter, means quantitative value about this, like we have this, that it has two frequencies. So from that quantity, that how many frequencies are there, I can conclude how many sine waves are there in the frequency and so on. So that is one of the feature, means this how many frequencies, number of frequencies, it is one of the feature with the help of which I can classify or I can determine what is the type of the waveform. Now look, coming to the image, if you look at these images, you can see that this, the texture of this, it is the smooth one, and the texture of this, it is the the texture is quite rough in this, means the pixel value in this one, it is quite similar to each other, whereas the pixel value over here, they are not much similar, right? So how we can classify without looking what may be the feature value that will tell us about the roughness of the surface without looking at the image. So if you look at this numbers, this number that I put over here, there are the standard deviation of the pixels that are present in this image, right? So if I determine the standard deviation, you can see that the standard deviation of this image, it is minimum. Standard deviation, it increases for this, it increases more for this, and standard deviation, it is maximum for this image. So what we can conclude, we can conclude that standard deviation can be one of the feature with the help of which, without looking at the image, we can determine what is the, whether the surface is smooth or rough, right? So it means that if I know this training, if I have this training about the feature standard deviation, so if anyone comes to me and asks me ask me that tell me whether the surface is rough or not, so simply what I am going to say, ask him, just calculate the standard deviation. The person is going to tell me the standard deviation value, and according to the value I can tell what about the roughness of the surface. So it means I do not need to look at all the pixel values. I do not need to see the complete image. Just a single value will help me to determine the type of the surface. And this is what help classifier also to make a decision. If we provide classifier with this type of a numbers, with the help of which classifier may easily predict, like simply if I make a threshold of 12, that if the value of standard deviation is less than 12, then we will consider the surface as smooth, otherwise rough. So simply by if else program, by writing an if else program, we can conclude about the roughness of the surface without looking at the image, right? So that is the power of feature extraction, and with the help of feature extraction, we just try to, we process the matrix and we try to evaluate some quantitative value, and with the help of which we may put some conclusion about the content in the image. There are large number of feature extraction techniques that are available, and the best thing, like the knowledge that we gain in our school days, like about the mean, standard deviation, median, skewness, like these all are one of the feature extraction methods. We can use this to get the prediction. Okay, and apart from this, like we can have Fourier transform, we have GLCM, local binary pattern, and there are large number of feature extraction methods available. And it is still an open research area because at the end, we want some feature extraction technique with the help of which our system, our classifier may predict with 100% accuracy in real time, means in minimum time. Now, extracting the feature, like because there are large number of feature extraction methods available. So how can we select which method is we should use for our images? So to decide that, we need domain expertization. Our domain expert, like suppose if I am working on a medical images, so we can try to ask the doctor that what type of features they look in the images. And if doctor tell us that they look at the number of horizontal lines, number of vertical lines, or number of circles present in the image, or something about the image, so accordingly, if we know about the background of these methods, that what type of feature they extract, if they extract the information about the horizontal lines or the vertical lines or the curves or circle or anything, so if we know about these parameters, then intuitively we can decide which parameter we should use. So one way is to get the domain expertization, talk with a domain expert, and then intuitively try to put the feature extraction method. And another way, because we have a program, so we can try if we can do a hit and trial method. Okay, but being an engineer, at the end we should know that why particular feature extraction method is working better in comparison to the other. Now, once we extract the feature, there may be a chance that the range of one feature, it can be between 0 to 1, and the range of another feature, it can be between 1 and 100. So the difference in the range may do some biasing, may put some biasing to the classifier. So to avoid that, we bring all the feature values or the range of all the features in the same range. Okay, so that one feature may not get dominate the other. Okay, so to do before giving these features to the classifier, we do data standardization. We try, like there are methods like min-max normalization. There are methods z-square normalization. Sometimes we also try to reduce the number of features that we have extracted. Suppose if one person extracted 100 features, another person is just extract 10 features, and with the help of 10 features that person is able to give a better classification results, then it's always better to, then of course we are going to use 10 features, not 100 one. So sometimes there may be a chance that whatever features that we have extracted, by doing some transformation, we can reduce the number of features. And if there are less number of features, then the classifier performance may be better in terms of computational time also. So how, like to give you the picture about this latent representation, how we can reduce the dimension. So just I have taken the example of PCA. So if you look at this, like suppose if we have a data set like this, and if all the samples they are aligned in this direction, so what we can do over here, if you look at this image, it is in 3 dimension: x-axis, x-axis, y-axis, and z-axis, right? So it is in 3 dimension. But when we put a samples when we plot a samples on this graph, then we have seen that all the samples, they are oriented in this direction, and the second orientation is this, right? So it means that the orientation or the distribution of the samples, they are only in 2 directions. So it's better to use only 2 dimensions instead of 3. So at the end, instead we will be able to reduce 1 dimension. So how we can do it? We can do a using the PCA transformation, we can change the orientation from this to this. And once we change the orientation, then you can see the distribution remains same over here in this image and in this image also. But over here in this, we are just using 2 dimensions. And over here, we are using 3 dimension. So since less number of features are used, so it will help the classifier. It will increase the performance of this classifier. So once we extract the feature, we should do our we should ask the domain expert that what type of features they are looking for. We should do data standardization. We should also try to reduce the dimensions of the features. Now the next is about the feature selection techniques. The feature selection, it is used to remove the irrelevant and redundant feature. So first of all, let's check what are irrelevant feature. Now, because the overall purpose of this, it is to make a classifier that is going to predict the type of the class, type of the or the class of the input image, right? So what it is going to do? Suppose if I want to train a small kid, and if I show that kid, I just want to train a small kid with a chair, that if it is chair or if it is table. So what I am going to do? I am going to show different chairs to that small kid, 2-3 years kid, and different tables to that small kid of different designs. So that, and I may also tell him or her that the chair may have armrest, backrest, and the flat area, it is little bit lower in comparison to this. The table should have flat area little bit higher, and there is no backrest or the armrest on the table. So I will tell these features about the chair and the table. But because suppose coincidentally, if I show the images of the chair that I have shown to the kid, if all are black in color, and the images of the table, they are all brown in color, so that small kid may find it more easy, more comfortable to determine whether it is chair or table. Like it will predict, it will take color as one of the feature, that if the color is black, then it is chair. If the color is brown, then it will be a table. So this feature, color feature, it is irrelevant and we should remove it. Okay, because it may misguide our classifier. Our classifier, when we are going to train it, it has the capability that it will automatically remove it. Means it will just give a 0 weight to that. But instead of asking our classifier or expecting our classifier for that, it's always better to remove all the irrelevant features that may misguide our classifier. In the same way as the color information is going to misguide the kid. So to avoid misguiding the kid, what we are going to do? We are going to tell the kid that, look, do not go with the color. Okay, it is just a coincidence that all the chairs are black, all the chairs are brown. It is just a coincidence. So at least by telling that, we are going to help him that do not predict whether it is chair or table with the color, because color is irrelevant information. It is irrelevant feature. Now the second is the redundant feature. The term itself indicates redundant means similar, that both the features, they are giving the same information. Now suppose if we have 2 features like this. Now since with time they are increasing in the same way, exactly in the same way. Only difference between these 2 is this distance, and this distance remains same everywhere. So it means that instead of 2 feature, I can simply remove one of the feature, because both the features are giving the same information. So simply I can remove one feature, so that it will be a feature reduction, so that unnecessarily I am not going to burden my classifier by providing the same type of features to the classifier. So this is that I should remove the redundant feature before giving the features to the classifier. Right? Now after having all the features, now before giving the features to the classifier, we need to arrange our classifier somewhat in this way. This is the data set. This is how we prepare the data set. That for the sample means the number of images, like image 1, image 2, and so on. And suppose for all the images, I extracted two features, mean and standard deviation. So for image 1, the mean and standard deviation; for image 2, mean and standard deviation, and so on. And thereafter, I in this column I put a class that all these images, like one select from 1 to 50, we have class 1 image, and from 51 to 100 we have a class 2. Means class 1 and class 2 means that class 1, it means it images of one type, class 2 means images of another type. Okay, you can consider it as images of a dog, and this class 2 has images consisting of cats, etc. So once we prepare our data set in this form, the first task then will be to divide our data set into two halves or into two proportions. Like one will be used to train the classifier, another will be used to test the classifier. This ratio, it depends upon the number of data that you have. If you have a large number of data, you can put a ratio between 70%, 30%, 70% in training and 30% in testing. So it is all up to you. But like the more data that we have for a training, the better classification or the better training to the classification may be there. So we need large number of data possible for training purpose. But this does not mean we may reduce the data set or the number of samples in the testing data set, because during the training, we are going to show to the classifier, we are going to give this input values, mean and standard deviation. We are also going to provide the class, whether image 1 belongs to class 1 or class 2, whether image 96 belongs to class 1 or class 2. So we provide this complete information. For the 60 samples, we provide this complete information so that machine or the classifier, it may train itself with this input and this output, and may decide that what should be the formula with the help of which the classifier may detect whether the sample belongs to class 1 or class 2. Right? Once we train our system, then testing data set is used to test the performance of classification. And when we are testing, it simply means that this data set, the classifier should not have seen this data set before. It should be new to the classifier, because if classifier has seen these samples before, then classifier will become biased. It is something like, suppose if we are teaching to our students and we are giving some numericals and some questions in the normal lecture classes, and we are also doing a solution. Now during the examination, if we give a same numerical, then there will be high chance that students will be able to do that particular question. But if we change, if in the examination, if we change the numerical, then the real testing will be there, that whether the student will be able to solve the numerical or not. So it is something like that testing data set, it should be new to the classifier, new in the sense that classifier should not have seen this testing data set during the training time. And once it is trained, we can then use the testing data set to check the performance of the classifier. Performance means in terms of the accuracy and other parameters. So now coming to the classifier, we have different classification models that we can use. Over here, I just give you the brief idea about the artificial neural network. So the artificial neural network, the best thing, like the things that we have studied in our 8th or 9th class about the graphs, the same concept we are using in the artificial neural network. So suppose if we have two features, like over here I am using on the x-axis marked as x0, y-axis I marked it as x1. So x0 is a mean, x1 is the standard deviation. So now if I plot all the training data set, the training data set that I have put over here, these 60 samples, if I plot this 60 samples in this graph, then if I just need to see if it is possible to have a straight line that may make a decision whether the class belongs to image, whether the image belongs to class 1 or class 2. Like over here, suppose if this green samples, they belongs to one category, this red samples, red dots, they belongs to class 2. Now over here you can see with the help of this straight line, it is a boundary, that boundary in such a form that all the green samples, they are located at the upper side of this boundary, and all the red circles, they are located below it. So what we can say, what we can conclude, we can conclude that if any sample lie above this line, then it belongs to this category, class 1. And if any sample belongs to lie below this line, then it belongs to class 2. It means that simply by I extract, like whatever sample I need to test, I will extract the mean and standard deviation. I will plot it in the graph, and if the point is located above this line, I will simply conclude that it belongs to class 1. Otherwise, if it is below, I will conclude it is in class 2. So overall, now you can see that the images, my classifier do not need to see the images in the same way we humans used to do. Classifier or this complete system will first extract the features like mean, standard deviation, and then with the help of this, the classifier will just try to get the equation of this straight line. Because once the classifier is able to get this equation, then with the help of this equation, classifier will be able to predict whether the image belongs to this category or this category. So you can see the equation, we can write as equation of a straight line somewhat in this way, where this x0 and x1, they are the mean and standard deviation, and this w0, w1 and w2, they are the parameters or weights of this neural network. And this weights is the parameters that classifier need to determine during the training time, during the training. So the samples, these 60 samples that we have put for a training, this, with the help of these 60 samples, classifier will try to get the value of w0, w1, w2, and once these weights are once the classifier is able to get these weights, means classifier get this equation. So now whenever we have new image, we extract the feature mean standard deviation, we just substitute it over here in x0 and x1, and w0, w1, w2 already we know from the training. So if the output, if the summation of this comes out to be greater than 0, we conclude that it belongs to class 1. If the summation is less than 0, simply we will conclude that image belongs to class 2. And suppose if the sample, if this x0, x1 or the point, if it lie on the line, then it means that our classifier is not capable to decide whether it belongs to class 1 or class 2. And in that case, either we will put a instruction for the user that classifier is not able to predict the class of this image, or we will just, it will leads to like misclassification, and it will, like the accuracy of or the performance of the classifier is going to decay. So we always try, or the classifier always try to get the line in such a way so that there is a proper separation of these points and these points. So this is the overall concept of artificial neural network. But for this, to get a single straight line, we use only one neuron. Over here, this is the assembly of neurons, artificial neuron. So it is one neuron. We put these samples like x0, x1. Over here, in our case, we have only 2. We do not have x2, x3. So x0, x1, along with the weights, is given to this. And we have one more thing, that is the bias. Okay, bias, the input will remain 1, but it has some weight. So w0, w1 and w2, like this, w0, w1, w2. So we give this and we get a summation. After summation, it will decide whether it is a thresholding, that it will decide like this, greater than 0 or less than 0. So this will decide whether the class of the image is this one or this one. So we get a summation, we get a threshold. But using a single neuron, we may get only a single straight line. But there may be a chance we may have this type of samples. Samples like if I plot the mean and standard deviation, there may be a chance that all these sample of one category, it comes in this, and in the remaining part we have samples of another category. So it is not possible to classify, or it is not possible for a single line to discriminate between the two category. So how we can do it? We can do it with a multiple straight lines. Like over here, we have three straight lines, 1, 2, and 3. And now with the help of these three straight lines, now if the sample lie inside this, then we can say that it belongs to class 1. If the sample lie outside it, we can say that the sample belongs to class 2. Now to replicate this with the help of artificial neural network, what we need? We need another layer. Okay, over here in the last case we use only single neuron. Single neuron give one straight line. So in this case, since we need three straight lines, so we use three neurons. And then these three neurons, the output of these three neurons is given to another neuron. And then this neuron will decide whether the class belongs to whether the image belongs to class 1 or class 2. So it means that the neural network or an individual neuron is going to give equation of a single straight line. But if the samples are clustered in such a way that it is not possible for a single straight line to classify, then we can have multiple straight line. And the equation of the multiple straight lines can be determined using hidden layers. Or we can have large number of neurons to put a enclosure. Okay, so even if a circle is required, so circle can be like, we can have small straight lines to form a circle. So again, neural network may work. So this is the overall concept of the artificial neural network that is used, and in the training time we just try to get the weights of this W0, W1, and W2, and so on. And over here I consider only two features. Suppose if there are 100 features, then the total number of weights, it will be from W0 to W99, means 100 plus 1 bias weight. So total 101 weights need to be trained. And it is the reason that if we are going to give minimum number of feature to the classifier, then performance of the classifier will be better in comparison to getting trained with a large number of feature. It is something like that for this image. If we have only one parameter, standard deviation, just with the help of one parameter, we are able to predict the type of the surface of the image. So why to have large number of features? And say in the same way, like it is easy for us to classify the texture of the or this surface of the image, in the same way, if we provide only one feature to the classifier, it will be quite easy for the classifier to get a training and to predict with 100% accuracy. So we should always try to give less number of features, but this does not mean that we may by giving the less number of features we sacrifice the performance of the classifier. So this experimentally we need to decide that how many features we need to provide. Okay, and so this is all about the classical approach that we used to do for the image classification. Now the same approach over here, if we look, that we have to decide in the classical approach, we need to decide which feature extraction technique we need to use. We need to decide which feature selection we need to use. Okay, but in the CNN model, everything will be done automatically. Means during the training, like over here, only this part we are training only this one. But in the CNN, we are going to train all this unit. Means all the parameters will be obtained during the training. So, and it is the reason because over here, if we include this also, the also in the training, so it will require large number of data, because now the system need to have the weights, need to have the values of large number of weights. So we need large number of data. So CNN can be used if we have large number of data set. Otherwise, if we have less number of data set and we are trying to use CNN, so it may not perform well. So now coming to what is CNN, convolutional neural network. So the convolutional neural network, the overall pipeline is this, that this is the input image. We provide this input image to this layer, we provide this input image to the convolutional layer and the ReLU. Then the output of this is then passed through the pooling. Then we may have another set of convolutional layer pooling. We can have any number of sets of convolutional layer and pooling. And once at the end, we are going to the last images that we are going to obtain, we then flatten them and provide them to the fully connected layer. This fully connected layer portion in the CNN, it is exactly same as this classifier. And this convolution and pooling layer, this portion, it is this feature extraction and feature selection. So in the classical method, this we were doing manually, we were deciding. But in this, the parameters involved in convolutional layer, that parameters will also be trained during the training phase. So that is the difference. So now let's discuss about this convolutional ReLU pooling one by one. Now about the convolution. So if I want to take the convolution of any image, this is the method. Okay, like suppose if this is my image and this is my filter. If I want to have the convolution of these two, so simply what I have to do, I have to put this filter over here. Okay, and then I apply this formula. Means I multiply this value with this one, this value with this value with this, and so on, and then I add them all. So whatever result that I got, that I will put in the output image, in the filtered image. So like when I put over here, I get this 0. When I put, now in the second time, I shift this filter by one position towards right. So previously it was over here. Now in the next, I shift this by one position towards right. So I get this, and corresponding to this, again I get 0 value. Now similarly, if I follow this, I get all zeros, right? Now when I come over here, once I finish this, I will shift my filter by one position downwards. So first I put my filter over here, and then I get value 0. Now I again shift it by one position towards right. And when I put it over here using the same formula, I get 3, and so on. So following the same pattern, I get the output as this. It means this filter, when I put this filter to all the pixels that are present in the image, I get this. Over here, you can note one thing, that the pixels that are at the first row, at the last row, pixels in the last column, and pixels in the first column, they are not involved in this operation, convolution operation. So the output image that we obtain, it is like we have number of rows, they are 2 less than present in the original image. Number of columns are also 2 less than the number of columns that are present in the original image. But that reduction in the number of columns and number of rows, that will not suffer much, because usually we have images of 100 by 100 or 200 by 200, 1000 by 1000. So even if it is 100 by 100, so reducing the number of rows from 100 by 100 to 98 by 98, it will not differ much. But we will be able to get some feature. So the convolution operation is this. Now, what are the impact of convolution? Suppose if I have this filter, Like over here, I use this filter values 0, 0, 0, 1, 1, 1, 0, 0, 0. But suppose if the filter values is this, then when I apply, this is the original image. When I apply this filter over here, then I get this image. And if you note that the sharpness in the edges that are present in this image, they got blurred. If I increase the size, like instead of taking 3 by 3 filter, if I take 5 by 5, the output is this. If I increase the size of the filter to 7 by 7, it is this, and so on. It is 15 by 15, 35 by 35. So you can see that the impact of this filter means the impact of this convolution that we have performed. It is on this image, it is this much. That as we increase the size, we are getting a blurred image. Okay, blurring, like in this case, it may give you a feel that applying the average filter is reducing the information. But suppose if there are some noise, if the image is noisy, suppose there are some unnecessary dots here and there. So if we then perform averaging, then that dots, amplitude of that dots or the amplitude of the noise, it may be suppressed. Okay, it will not be removed completely, but it will be suppressed, right? So that is the reason that average filter is used for the enhancement purpose. Now the same convolution, like if I change the filter, like suppose if I am using this filter, value of the filter is this, applying the same operation of convolution, this is the original image and I get this. And you can see just by changing the filter, the values of this filter, now I am getting the edges that are present in this image, right? So that is the power of convolution, that the operation is same, but just by changing the filter values, we are getting different information in the output image, right? So it means that when, like in over here in CNN, if I use different filters, then different filters may give me different information. But how to select which filter I should use, how to select these values? So in classical method, these values we decide on our own, we decide manually. But in CNN model, this and when I say manually, it means mathematically proved. Okay, with some mathematical logic, we are using this value. But in CNN, these values are obtained during the training phase. So means we do not have any control about these values. CNN trained itself and also trained these values so that at the end, CNN should be able to classify whether the image belongs to class 1 or class 2. And also remember one thing, like transforming the image from this to this. Now, of course, this is better image instead of in comparison to this. But since the overall purpose is, suppose if I want to determine whether the image consists of a camera or not. So overall, my purpose is just if camera is present or not. I do not want any other information. So what the intermediate steps that are involved, or in the intermediate steps, if I distorted the images, then also it is okay, because the main thing that is required, it is the output, whether my system is able to classify whether camera is present in the image or not. That is the thing that is required. So even if we distort the image, distort in the sense, if we remove some of the information, like over here we remove these textures, this here texture over here, this coat over here, color of a coat, so we removed it. Okay, but it still help us to classify whether the camera is present in the image or not. So in CNN, we use large number of convolution layers so that we can get different information, like we can have the edge informations, we can have this type of information also, and so on. So, but the training is done by the in the training phase only. So if we select n filters, then applying n filters on the image will generate n output image. It means, suppose if I have this single image, if I use n convolutional layer, so after applying n convolutional layer, I will get n images. Okay, and each output image will consist of different features, like it will have features like edges, it may have features like color or some texture or so on. Now, In CNN, the weights, this I already discussed, that it is adjusted, the weights of the filter are adjusted during the training of the CNN model. And it is one of the major difference between the CNN and the classical method. Now coming to the next, ReLU. Now what ReLU is? ReLU is a function that has this relation between the input and the output, that if the value of the input, if it is negative, then ReLU function is going to make all the negative values as zero. And if the value of the input is positive, then it is going to make all the values as positive. It will keep it as it is. It will not change it. Like suppose if we have this image, we apply this filter on this image, we get this one. Okay. Now on this filtered image, means after the convolution, when we get this image, so when I apply ReLU over here, then after applying ReLU, all these negative values produces this output. But when this output is given to the ReLU function produce this output. And you can see in this image we have one horizontal line, we have one vertical line. Now when I apply this filter and passing through the ReLU function, I get this thing. And like from this I can have some impression that at least like it is giving me some idea about the horizontal line. Okay, vertical line information is missing. So we may say that this filter is used to detect the horizontal lines that are present in the image. Right. Now the next layer that is there, it is pooling. Pooling is usually used to downsample, means to reduce the size of the image. And the main purpose of the pooling is to select the prominent features from the output image. Like over here, after this is the image that we obtain after applying ReLU function. Now after when we apply pooling, so what we do, we just make a group. Like we make a group of 2 by 2 pixels. So 2 by 2, 2 by 2, 2 by 2, 2 by 2. And then out of this, if we are using max pooling, so we will simply in the output image, we will simply select the maximum value in this. So over here the maximum value is 4, so I copied 4 over here. Over here the maximum value is again 4, so I copied over here. It is 0, so 0, 0, so 0. So you can see that with the help of max pooling, we are able to reduce the size of the image, right? And while reducing, using the pooling, we are just trying to get the prominent feature. If we are using the max pooling, we are just trying to get the feature that has the highest amplitude. Highest amplitude means that that feature has a dominancy in comparison to the remaining pixels, right? Suppose if we want to classify like texture, if texture is important in our image, then we can also have the average value. We can take the average value of this, like 3 plus 4 plus 1, it is 8 divided by total number of pixels. So 8 by 2, we can have 2 over here. Again, it is 8 plus 2, 10, 11 divided by 2, round off. If we're taking the round off value, it will be 3. It will be 0 and 0. So overall, pooling, whether we want to use max pooling or the average pooling, it depends on the type of the image that we are processing and the type of the information that we are looking for. Now, after the pooling, the next operation that we need to perform, it is the flattening. And in flattening, simply we convert our multi-dimensional matrix into a single dimension vector. What it means? It means that the output of the max pooling, it is this, right? Now, the output, this output will be transferred. This is a two-dimensional image. So this two-dimensional image will be converted into a vector form like this. Means simply the first column value I copied over here, and just below it I copied the value in the second column. So this operation, it is known as flattening, means converting the multi-dimensional image into a single vector. And then this single vector will then be provided to the fully connected layer. Means the ANN, artificial neural network. So this is our fully connected layer, and the output of this flattening, the output is then provided to this input neurons. So I provide this value to this neurons, and then accordingly I get the class, whether the image belongs to this class or this class or this class. So this is exactly the same that we have discussed in the classical method. So this is all about the CNN and the classical method. So now let me demonstrate the Python code that we can use for the implementation of CNN model. Uh, is it okay? I need to share my screen again. Is my screen visible? Okay, so let me share it again. So participants, please mute yourself. Uh, Okay, so this is the over here. Like even if you do not have a like background of Python, so I will try to clarify what statements I have put, so that like it may be easy for you. I will share this code in my YouTube channel as well, and I may share this to the Dr. Saurabh also for your reference, right? So over here, like when we over here, the Python implementation I have done in Google Colab, and so in the in Python, first of all, we need to import some libraries, and to import the libraries, simply we put this. Okay, it is with respect to the neural network, that CNN model that we need to prepare. So Keras consists of a library that with the help of which we can develop or design the CNN model. NumPy, it is used to manipulate the array. Matplotlib, it is over here we are using it to display the images, and this Seaborn, it is used to display the or to visualize the data set. Okay, data set means ki, like how many samples are there in different samples in different classes. So the first operation that we need to perform, it is the how we can load the data set. And over here I simply use the data set that is there in the Keras. Okay, so there are some data set available in this package. So I simply use that. I simply load that particular data set. We can also import our data set from the Google Drive. So simply if you click over here, so it will simply mount your Google Drive. Okay, over here, and then you can select the path, and from there you can do the you can get your own data set over here, right? So but I will not discuss that due to time restriction. So simply when we call this particular function, this Keras, it is the library that we have imported over here. So in this library we call the method dataset, and in that dataset we just mention that we want this dataset mnist. It is a dataset consists of numbers, digits, okay, from 0 to 9, and there are huge, the dataset, it consists of huge number of samples for different digits, right? And then we simply call this function load data. So with the help of this, we will be able to import the data, and the data that is present over here, it is already divided into the testing and into the training. So we do not need to divide the data. Already it is divided. So if I execute this, okay, first I need to execute this. So executing this, I am just simply importing all these packages. Now if I execute this, it is going to import the dataset. You can see that it is downloading the dataset. And if I want to see if this dataset, like what are these datasets, so simply I will click over here on this, and this is a variable inspector. So over here I can check, like you can see that if I put my cursor over here, it is giving that the shape is 10,028 by 28, means there are 10,000 sample and the size of the image it is 28 by 28. So we need to know about the dimensions of our data set. So if I like similarly, if I check about this IMG train, so in the training we have 60,000 samples, in the testing we have only 10,000. This label test, it is the class, you can see 10,000, the size is 10,000. It provides the labels, like over here the first sample it is of digit 7, second sample it is of digit 2, and so on. So this label test, it gives the information that what is the class of the input image. And similarly for this training it is 60,000 samples, like it gives a label for the 60,000 samples. Now we have a command, this img.train. So like you can see over here, it is nd array. Nd array means that it is a numpy array. Or numpy array means that all the functions that are available over here, I can use that function. So one of the function that is there in the numpy array, numpy is the shape, that with the help of this I can determine the shape of my matrix. So when I simply print, when I simply try to print or display the information of the shape, so I get this information. So it means first dimension it is of 60,000, second dimension it is 28, third dimension 28. So same information that is there in variable, but over here in variable inspector I have to see, but over here programmatically I am able to determine. So because at the end we need to automate the complete thing, so we should put the program code so that everything should be programmatically done. Now after that I am just displaying one of the sample like 80 over here with this code, with the help of this function plt imshow, I just display this particular image of sample number 841, and this sample, and with the help of this I provide a title that I have provided is that what is the label of that particular sample. So we have, like over here we have two things, img train it is the input, this label train it is the output that is expected, means that whether the digit is 0, 1, 2, 3 or so on. So over here I display the image, this image, and then I give a title to this class label, and this is the title, means the class label is 6. So you can see label is 6 and image is also of 6. If I change it to something else like 8411, now I rerun it. So you can see now it is giving a shape of 2 and the class label is also 2. So this is just for our thing that we just want to check if our data set, if it is proper or not. After that, we have a command np unique. Np unique, it simply give us all the unique values that are there. Okay, like over here when I put np unique, it give me the unique values. How many unique values are there for sample 4 digit 0? How many samples are there for image 1? How many samples are there for digit 2, and so on? And the unique values, what are the unique values? So over here I execute this particular code and I get a count, number of samples in each class. I get a class label in the unique, and I also put this formula np.sum count. So it simply take the sum of all these values. So the sum of all this value, it is 60,000, and with this I just confirm that the total number of samples that are present in my this label train 60,000, same I am able to get this. And the same thing we can visualize if I execute this, same thing we can visualize using the this particular Cbone, this particular package. With the help of this, we can visualize it in the form of a bar graph. That digit 0, it has this number of sample, digit 1, it has this number of samples, and so on, right? Now, the next step that is required is pre-processing of the images. Now, in CNN model, since most of the things is done by the CNN model itself, like in the training phase, it do it itself. But sometimes it may be like we may do some pre-processing, like in the sense that we may need to make the size of all the images equal, or we may need to enhance the image to some particular level. So that pre-processing may be required, but it is not the very necessary step in CNN model. Okay, but the size of all the images in the training and the testing data set, they should be same, exactly same. So if they are not same, then we need to pre-process the data to make them same. Third step that we need to do, it is to split the data into the training and the testing data set. And this, since in our case it is already divided, so we do not need to perform this. But I have put a code over here that if we want to divide, if the data set is not already divided, we can divide it using this particular command, right? Now the next thing, and that is the most important thing, it is how we can design a CNN model. Now to design a CNN model, we need some library again. So I simply execute all this. Okay, I import all this. And now when we are designing a CNN model, so the way, like if you look, just a minute. If you look at this particular image, like we have convolutional layer, we have ReLU layer, we have pooling layer, right? So simply we need to decide how many convolution layer we want, how many pooling layer we want, when we want ReLU layer. So simply we need to, according to that requirement, simply we add the layers. Means like over here, when I call this function, CNN1 equals to sequential. So over here, I am just giving instruction to the interpreter of the Python that I just want to have a sequential CNN model, and in the with the name CNN1. So it will be the name of my model. Now in the second line, when I add CNN1 add, so over here con2D means I just want to add one layer of convolutional, two-dimensional convolutional layer I want to add. So, and the dimension or the description of that two-dimensional convolutional layer that I provide over here, that I want convolutional layer, my convolutional layer, it should contain 4 filters. The size of the kernel, it should be 3 by 3 as, sorry. Over here. So over here with this, I just tell the interpreter that I just want to design a sequential CNN, that I will just simply add the layers, and rest this interpreter or this Keras library, they are going to do their own. So I am just instructing that the name of the model, it will be CNN1. In the next, CNN1.add. With this command, I am just telling the interpreter that I want to add some layers. The first layer that I want to add, it is the convolutional layer, two-dimensional convolutional layer. And the parameter, I also need to provide the parameters to that convolutional layer. So over here, when I say filter equals to 4, it means I want 4 convolutional layers to be added. The size of the convolutional layer, it will be 3 cross 3, as we have used in the PPT. Then stride means stride means that when we over here, when we perform the convolutional layer, so we shift this filter. Initially it was over here, then we shift this filter only by 1 position towards right when we come over here. So we can say that the stride is 1, that we are shifting only by 1 position towards right. If I put stride equals to 2, it means that initially I will start from here, but if stride is 2, then I will not shift by 1, I will shift by 2. So instead of coming to this, I will directly come over here. So stride defines the amount by which I want to shift my kernel during the convolution time. Now the now the padding. Now the padding means that, as we have discussed, that while performing the convolution, the size of the input layer, input image, and the size of the filtered image, it is changed. Okay, it changes because we are not able to put this filter on the top row, last row, first column, and the last column. So due to this, the size of the output becomes, it reduces. So to avoid reduction in the size, what we can do, we can do a padding. With padding, the size will remain same, and simply in padding we can either make this values 0, means the rows and the columns on which we are not able to implement convolution, we simply make the value 0, or we simply make copy the values of the first rows, last row, first column, last column. We simply copy this value in the filtered image as it is. So depending, it all depends on our requirement. So over here, padding equals to same. It means that the size of the input and the filtered image, it should remain same. Next is the activation. Over here, we provide, I put relu. It means the activation. It means that I want to provide, like, the after the convolution, I want my output image, my filter image, to process using relu. So after the filter image, relu function should be implemented, and the result should be this. Result. I will get this type of a result. And then the input shape. With the help of this, I just decide that what will be the size of the input images. So if I put 28 by 28, it means that if I try to give any image of size different than this, means suppose if I try to give image of size 40 by 40, then it will simply produce the error. It will not accept it. So if I want to use this CNN model, the inputs of the size of all the images, it should be 28 by 28. So over here, I am deciding what will be the size of the input image. So overall, with the help of this layer, I am able to add one layer, and in that layer, I just do a configuration, and that layer is the convolution layer. After adding the convolutional layer, the next is the pooling layer. So again, I ask the interpreter or the Keras library to add another layer, and this time the layer that I want to add, it is the max pool 2D. Okay, and again I provide the configuration, the pool size, that how many, how I want to group the pooling. Like as we have discussed over here, we have group 2 by 2. But if I provide 3, then I will group 3 cross 3. All these pixels will be grouped to create a pooling, right? So the pool size and the stride value, and then after that it is a dropout. Now over here, like in this, it's also, I just put a link also which help you to give some idea about the dropout. So dropout simply means that the output that we output that we obtained with these layers, some of the outputs we simply reduce it to 0. We simply reduce it to 0. We are not going to provide it to the next layer, and by doing so we are able, by some number of layer output are randomly ignored or dropped out, and this has the effect of making the layer look like and be treated like a layer with different number of nodes. It means over here I select the dropout as 0.25. It means that randomly it will select some of the output from the previous layer, it will make it 0, and it will not provide that output to the next layer. By not providing it to the next layer, simply what we are saying, that the node values corresponding to this, we are not using that node values simply. So with the help of dropout, we can avoid overfitting. Overfitting means that like there may be a chance that the classifier, with the help of the training data set, classifier is able to predict with 100% accuracy. But if the classifier is not performing well, or performs really very poorly in the testing phase, so we can conclude that overfitting is there. So to avoid that, we use dropout. Then after that, if we want to add more number of convolutional layer or max pooling, we can add it after this. And at the end, then we are first going to do a flattening. So again, we call this that we want to add another layer with the name flattening. We do a flattening. Then that flattening is then provided to the dense layer. Dense layer means the is ANN model that we this dense layer. So this is the first layer of the fully connected layer that we want. So we provide this, and then again a dropout, and then again I added another dense layer. Means I provide, like, first is this, second is this. So I use two dense layers. Okay, so over here I have used two dense layers, and dense layer over here 256 means that the output of this flattening means we just create a vector. So the output, this vector will be provided to 256 neurons. Okay, means like this. It is the flattening. This output, this values will be provided to these neurons. So by writing 256, it means that we will be having 256 such type of neurons. And then we put another dense layer with number 10. That 10 means that we have another dense layer, and the number of neurons that we have, it is 10 in number, right? So with this, we design our CNN model. We added all the layers. And the best thing with the Keras model is that with this library, simply like we do not need to worry how this convolutional layer or max pooling, how they are going to perform. Simply by using this, we can add any number of layers and any type of layers, like convolutional, max pool, or dropout, flattening, dense, like we can add anything, right? So if I execute this, so it executing means that it has created the CNN model, and I can check in this that over here CNN1 it appears in, and the type is sequential. Now after that, we have one command CNN1.summary. If I execute this, it is going to summarize our CNN model. And you can see over here the convolutional 2D. The first layer is 28 by 28 into 4. So, and if you remember that over here, the convolutional layer, in the convolutional layer, we added 4 filters, and the input image is 28 by 28. Padding is same, means the size of the input and the output, it remains same. So the output of this layer, it will be 28 by 28 because the size of the image is 28 by 28 into number of filters. So the output of this layer, it is 28 by 28 into 4. And total 40 parameters we have trained. How 40 parameters? Total, like the size of the kernel, it is 3 by 3. Means total 9 parameters are there in each and every convolutional layer. And along with 9, we also have one bias in the convolutional layer. As we have bias in the ANN. Similarly, we have a bias in convolutional layer also. So along with this 9, we have one for the convolutional layer. So total 10 parameters need to be trained for each and every convolutional filter. So since 4 filters are there, so 10 into 4, we get total 40 parameters. So over here, this represents how many parameters need to be trained in this particular layer. After that, the next layer is max pooling. Since we have used 2 by 2, pool size is 2 by 2. So it means that the size of the image, it will be reduced to half, right? So input this convolutional layer when provided to this pooling layer, we get output as this, right? And since in the pooling there is no parameters that need to be trained, so the parameters involved is 0. Then the dropout. Dropout simply means that we are going to ignore some of the parameters, some of the output of this. So the size out of the output image, it remains same. Then flattening. Now whatever the result, this output, we have just this multi-dimensional matrix, we convert it into the single vector, one dimensional vector. So the total, if I simply, like over here I have put this number also, 14 into 4 into 4. Over here, this, if I simply put a multiply this, okay, so I get 784. So after flattening, the output will have total of 784 values, as we have discussed in the PPT, that after pooling, when we do a flatten, simply flattening means that we copy all the column one under another. So by doing the same operation over here, we are getting a 784 values in the vector. Then these values are then provided to the dense layer, and in the dense layer we have 256. So all these values, 256 means 256 neurons. So it means then 784 values will be provided to all the neurons. Plus, along with this 784, we also provide one bias value. So it means 785 values will be provided to each and every neuron, mean to all the 256 neurons. So total, in all, we will get all these parameters. 2,960,000 parameters need to be trained by the CNN model. And this value, for this value, I have put over here that this is the number of values that we have in our vector into number of neurons in first dense layer plus the number of bias values that is required. So in total 20960 parameters are required. And then the next layer in the dropout, we do not need any parameters, so it is 0. Next layer, in the next layer we use 10. In the last layer we use 10 neurons. So it means that all this the output of this 256 will be provided to 10, to all these 10 neurons. So this 256 plus 1 bias, so total 257 values are there that will be provided to all their 10 neurons. So total 2570 parameters need to be trained, and overall the summation of all these parameters, it is 20357, 2,03,570 parameters need to be trained with the neural network, with the CNN. Okay, and it is this number which requires huge data set. If we do not have huge data set, then it will not be possible for our CNN model to train all these parameters that will produce better results. Okay, so, and it is the reason that if we try to perform this type of computation in our normal computer with CPU, it may take huge time. Sometimes it may take days also. So for that we need GPUs. And in this Google Colab, if you go to this runtime and change runtime, you can select off from here GPU. So Google Colab also provide this facility that we can simply select, we can run our code in GPU, but that GPU which is present in the Google server. So after that, once we design our model, next task is to compile our CNN model. Okay, so to compile, first thing we need to provide is the optimizer. Type of the optimizer that we want to use. So the optimizer simply means that with the help of the optimizer, we update the weights of the neural network. So the parameters that are involved, like these parameters that are involved, so we need to update their weights, their values during the training phase. So how we are going to update, that will be decided with the type of the optimizer that we are going to use. Over here I have used Adam. Adam is considered, like in most of the research paper, Adam is considered as one of the best optimizer, but again it depends on the type of application that you are working on. But in most of the application, Adam has produced the better results. Now, once so we have decided the optimizer, we also need to provide the loss function. Loss function means it will give you the like the difference between the expected result and the result that we obtain. So what is the difference? What is the loss? Suppose if I am expecting the value to be 1, but I get only 0.5, so the loss is of 0.5. So that loss need to be calculated, so that according to this loss, then my optimizer is going to update the weights in such a way so that this loss can be minimized, so that the optimizer can reduce these weights. So we need to provide that what type of loss function we want to use. So there are different loss functions that we can use. So again, it depends on the type of the applications that we are working on. And after along with this loss, we also need to provide the metrics, and this metrics, it is the performance measure, like how we are analyzing our model. So over here I have selected the accuracy, but we have other metrics also, and I have provided the link over here. This will give you the complete like list of all the metrics that you may find in this particular package, Keras. Okay, so with this, after selecting all this optimizer, loss, and metric, now we can compile our CNN model. So I have to run that, and then this. So now I have compiled my CNN model. Now the next operation that I need to do, I need to train my CNN model. The model that I just compiled, I need to fit it with the training model. So means the updation of the weights will be done in this training of a CNN model. So to train the function that is there in the Keras, it is fit. With the help of this function and by providing this parameter, we can do a training of our model. So if I simply click over here, it is going to do a training. Okay, over here, like this batch size. Batch size means that it is the number of images that we are going to process before updating the weights. And epoch means that epoch 5 means that if I have 60,000 samples in the training, then 60,000 samples will be used for training 5 times. So there will be a 5 iterations. So you can see in the first epoch, loss is this, accuracy is this. In the second epoch, loss has reduced from 4.5, it reduces to 0.9, and accuracy has increased from 0.59 to 0.73. In the third, again, it has loss has reduced. So you can see with epoch, loss has reduced. And same thing we can display using the graph. So once it runs completely, it is taking some time. Let this be completed. Okay, now it is run, and the same thing, like the graphically we can represent like the validation loss and the accuracy. So we can represent graphically that how with the number of epoches, how the loss has reduced, and this red, it is showing how the accuracy has increased. Okay, so means exactly the same thing that we produce over here. Same thing can be graphically represented. And once we have now we have a trained model, this net, this is a trained network. Now we can use this trained network for a testing purpose. So for testing, simply we have a function predict, CNN1 predict. So we provide our testing data set into it, and we run. So all the testing input images will be provided to this, will be taken as input, and that input images will be then applied to the trained network, and it produces the result. Means it produces like which sample of the test image, which sample belongs to which category. And now after that, with this we need to, like, when we are testing is the thing that which tell us about the performance of our model. So over here I just using the confusion matrix, I display that, like, over here on the y-axis it is a true label, and it is on the x-axis it is a predicted label. Means if it is 9, actually this is this number indicates number of samples. So over here this 4 means that 4 samples are such whose actual class is 9, that the digit is 9, but our system, our model has classified them as 0. So it is a misclassification. Our classifier has performed as misclassified, as predicted wrongly. But and this green, they indicates that the true label is that 965 samples are such whose class is 0, that they show digit 0, and they have predicted, our system, our model has also predicted them 965. So out of 9 so 965 samples, they are classified correctly, and this 5 plus 4, sorry, this 3 1 11, total 14 15 16 17 samples of digit 0, they are misclassified. Misclassified as 11 is samples are classified as 8, 1 is classified as 7, and 3 samples are classified as 6. So with the help of this confusion matrix tell us the everything detail, that actual class is this and what our system has predicted. And with the help of this confusion matrix, we can decide, we can check that why, what may be the reason that this 0 is classified as this 8 7 and 6. We may try to have some engineering intuitive or engineering concept logic into it. So so this is that we predicted, we just check the performance of our system. And our system, like 965 total, suppose if there 1000 samples are there, so the accuracy is around 96 to predict 0. Accuracy is around, like, we need this is not the accuracy, so we need to divide this sample with the total number of samples that are present. So the accuracy, if I simply add all these samples divided by the total number of samples in the testing data set, so adding all this divided by the total number of samples in the testing data set will give me the total accuracy of my system, and that accuracy will be, like, over here it is the training accuracy, okay, the accuracy that we obtain during training. But the performance is measured with this accuracy, the accuracy that we are going to obtain by adding all this green squares number divided by the total number of samples. That will give the actual performance of the system. Now, last, I am just going to display the output of each and every layer of the CNN model. Means the just a minute, input, I am sure is got right there. Okay. Like what are the output after the implementation of convolution, after the implementation of pooling, and so on. So over here I have selected this sample 8411, and with the help of this I just I will be able to, you can see after the output of layer 1, it is showing this, output of layer 2 is this, output of layer 3 is this, and what are these output layer 1 2 and 3. So if I look at the summary, so layer 1 is this convolutional layer, so the output of layer 1 means the output of convolutional layer, output of layer 2 means the output after applying pooling, and the output of layer 3, it is after the dropout. So you can see that this is the output that we obtain after convolution, after pooling, and this is after the dropout. Okay, and means this information we provide to the neural network, artificial neural network after flattening. And our artificial neural network is able to predict the class, whether it is 2 or 1 or 3. So it is able to predict just with this information, right? So so this is all from my side. So so any questions, and you can connect me with my YouTube channel or LinkedIn, or my email ID is this. So any question, anyone?
Thank you so much, sir. That was actually a great explanation on CNN models and how we have to implement these models. Sir has demonstrated using Google Colab uh, how we can use CNN for extracting the features as well as for extracting the knowledge from the images. So I think, sir, there are few questions in the chat box. So you are requested to address these questions.
Yeah, let me read them. Uh, uh, Dr. Manjoor has asked if we have multiple classes in the dataset, at that time, which classifier we should use. Like we can use artificial neural network also. You know, like it depends. Actually, it depends on the type of the information that is there in our data set. Okay, but most of the time, like this artificial neural network or decision tree, or they works properly. So next question is there any tools to draw ANN result? uh, like ANN result, I guess you are asking what I have displayed just now, the results that in the intermediate step and the summary of the CNN and so on. Is it right?
Anyone wants to interact with sir, so just unmute yourself and talk to sir directly.
Okay, so next question is there any criteria like every class has to contain same number of samples? Like during the classification, it is always better to have a balanced data set. Balanced data set means that we should have almost or equal number of classes, equal number of samples in all the classes. Because suppose like if I have a data set in which, just for a simplicity, let's take an example that suppose if I have a data set having two classes, and for one class I have 1000 sample, for the another class I just have 10 samples, okay, or 100 samples. Now suppose in the testing data set, now suppose I train my classifier and my classifier is able to predict only class 1, means I provide any image but it is just providing only one output, class 1, and it is not able to classify whether there is any image of class 2 or not. So but since only 100 samples are there of class 2, right, so the accuracy of my system is still, it will be around 90%. Okay, so even my classifier is not able to classify, or it is not trained at all properly, but still it is showing 90%, right? So for that, we should have a proper number of samples, almost equal number of samples in all the classes.
Okay, thank you, sir.
Next is it possible that you share, I will not be able to share the presentation, but I will definitely share the code. Okay, in my GitHub I will share it, and I will put it in my in the description of my in the description of this YouTube video, plus I will also share it with Dr. Saurabh.
Sure, thank you, sir.
And please share the Google Colab. Okay, thank you. Do PCA can be applied? Abhishek, I did not get the question. Do PCA can be applied? Okay, so next question from Dr. Anju. Which network is suitable for handwriting recognition? Like the best thing about the CNN model is that we just want to create a number of layers. right? So for the handwriting recognition also, like CNN model, as far as I know, it is working with good performance, with good efficiency, you know. So like you can use that CNN. So any other question, anyone?
Can we do trend prediction in fashion? This is one
Sorry,
more question. One more question is
trend,
there.
we can do trend prediction.
Trend
Yeah,
prediction.
yeah, we can do, but trend prediction, it comes it under the category of regression. Okay, but of course we can do it. And the pipeline is almost same with little bit difference. Like in prediction, like we in classification, we can have values either class 1, class 2, class 3, or so on. We But in prediction, in regression, we can have any value in between, like in between 1 and 100, we can have any value. Okay. uh, we can, question is, we can do it in AI or ML. So like ML is best for it. Okay, but AI and ML, in fact ML is a part of AI, right? Because like whatever is there in ML, it is the part of AI. AI is a big picture, and out of that big picture, ML is the sub part of AI. So to me, like both are same, but AI includes more things what ML does not have. But ML is best for the prediction and for the classification.
So this is actually the proof of the lecture was really very wonderful. That's why a number of questions were raised by the participants. So that's why when the lecture is good, though at the same time we expect good questions from the participants, and at the same time I think uh, sir has presented in such a way that even the freshers who don't know about the CNN and how to classify the images, so even freshers can have the great knowledge from this lecture, and definitely they will implement these things by the guidance of Dr. Nishant Jain. So once again, I am very thankful to you, sir, for sparing your valuable time and for a quite knowledgeable session in this 1 week FTP on machine learning concepts and applications. Thanks a lot.
Thank you, Dr. Saurabh, and thank you to all the participants for listening to me from the last like almost 2 hours. So thank
Yeah.
you so much.
Thank you.
Thank you.
So, dear participants, this was the first session, very informative session delivered by Dr. Nishant Jain. And now we have another session at 2 p.m. I have shared the details in the WhatsApp group already. So we'll meet now at 2 p.m. Uh, the session, the next session is on machine learning and multivariate signal processing for medical applications. And Professor Ram Bilas Pachori from IIT Indore, he will join at 2 p.m. So thank you very much and have a nice day. Thank you. Attendance link is already shared in the chat box as well as on YouTube and the WhatsApp group. Thank you.